All right, welcome back everyone for another deep dive. And today we're looking at something that I think is really exciting, getting computers to write their own software. And this isn't just like little scripts or anything, we're talking complex software and doing it reliably too, which is a big ask. It's actually an old idea. Researchers were dreaming about this as far back as like 1971. There's this early work from Manna and Waldinger. And I think the core idea back then and now is pretty clear to like take some of the load off of us, the human software developers.
Yeah, absolutely. And a key thing to keep in mind with all the progress that's happening in this field is this focus on interpretability, right? So it's not just about having, a black box machine learning model that spits out code that we don't really understand or can't easily change.
Right. Yep.
There's a really strong push towards program synthesis. And this is something Bostani and his colleagues highlighted really nicely in 2022. And basically the idea is that, this allows us to actually understand the AI generated code, validate it, and even edit it, which is really powerful.
Yeah.
And, this becomes even more important as we start thinking about using these techniques in much more complex and sensitive areas, right? So you can think about things like embedded systems. So there's this paper from DARR and others in 2021. Or even healthcare, like Connolly and others in 2023, and also Gia et al. In 2022. They've all touched on this.
Right, yeah. Makes sense. The higher the stakes, the more you want to understand exactly what the code is doing and why it's doing it.
Exactly. And the method to actually achieve automatic programming had really evolved over time, right? So we started off with more formal approaches, deductive approaches. You can think of Allure and others in 2015, and built on earlier ideas from, going back to Manna and Waldinger in 1992. And then we saw the rise of genetic and evolutionary methods. There's a great paper from Vadim Levancev and colleagues in 2019 that explores that. And most recently, I think the thing that's really changed the game is this explosion of large language models, or LLMs, trained on these massive code data sets. Zhu et al. In 2022, Zhan et al. In 2023, they all demonstrate these incredible capabilities, especially with zero-shot generalization, as shown by Chen et al. In 2021b.
Okay, so that brings us up to speed on like the sort of state of the field and the different approaches. And as always, we've got a listener who has shared a really interesting paper with us that directly tackles this core challenge of like, how do we make computers program themselves reliably and to create like, truly complex software autonomously. So the authors of this paper are Anastasia Grasina, Vadim Levancev, Aki Harma, and Leon Mounin. And they actually just published this work in February 2025 in the ACM Transactions on Evolutionary Learning and Optimization. And the title, I think, is actually pretty descriptive here. It's called Fully Autonomous Programming Using Iterative Multi-Agent Debugging with Large Language Models. So that really sets the scene for what we're going to be digging into.
Yeah, definitely.
So what is our mission with this deep dive?
I think our mission today is to really get under the hood of this paper, right? To unpack those key ideas that they're presenting and really explore this innovative framework that they've developed, and ultimately try to understand what it could mean, for the future of software development. And I think a big part of that, and a really unique aspect of this work, is that they're leveraging LLMs not just to generate the initial code, but also to iteratively debug it and refine it, which has traditionally been a major bottleneck in this whole process.
Right, yeah. I mean, I can totally see that. Like, even if an LLM can spit out code, getting it to be, like, perfect to pass all the tests, that's a whole other challenge.
Exactly. And, as Bavishi and colleagues pointed out back in 2022, even those really cutting-edge LLMs, they often struggle with producing code that actually flawlessly compiles and passes all those tests. And so often what you end up with are what we call near-miss solutions. It's code that looks like it should work, but in practice, it just doesn't quite get there. And so this paper really tackles that last mile problem head on, which is a really critical step for making autonomous programming, truly autonomous.
Okay, so they're trying to solve this last mile problem of getting the code from almost working to completely working. So what are the key innovations that make this whole thing like more tractable?
Well, they're actually building on two really important advancements that have happened recently in this space. The first is the synthesize, execute, debug framework, which Gupta and colleagues introduced back in 2020. And the second building block here is this amazing progress that we've seen in instruction, but finally fine-tuned large language models, which Zhang et al. Discussed in their 2024 paper. Mm-hmm. So these are models that have shown a lot of promise in tasks like, automatically repairing errors in code, and Fan et al. explore this in their 2023 paper. But the authors of this paper correctly point out that there's still a lot we don't know about the best way to instruct these models for, optimal repair. So it's not just about having these powerful models, it's about knowing how to talk to them to get the best results.
Yeah, that's fascinating. So it's like you have these amazing tools, but you need to figure out how to use them effectively, how to guide them towards what you actually want them to achieve.
Precisely. And that brings us to the core contribution of this paper, the EIDR framework, SEIDR, which stands for Synthesize, Execute, Instruct, Debug, and Rank. And as you'll see, it's really about breaking down that process of autonomous programming into these distinct stages. And what's really neat here is that they're actually building on their earlier work from their GCOGO 2023 paper. It was a paper with Levancev and others. And the core idea is to use this multi-agent iterative approach where each agent has a specific role in the overall process. And they use feedback from actually running the code and seeing which tests fail to guide that whole improvement process.
Okay, so it's not just about generating code in one shot. It's about iteratively improving it based on feedback.
Yeah, absolutely. And I think it would be helpful to kind of break down these core agents within SEIDR as they illustrate it really nicely in figure 1 of the paper. So it all starts with the synthesize agent. This agent is responsible for generating the initial candidate solutions, and it does that using an LLM, which they denote as synth, and they provide it with a task description, some input-output examples. You can actually see how these are structured in figure 2, and all of this is wrapped within a predefined code template. And what's really interesting is that they use something called spring sampling, which is a method to encourage diverse code generation. So the idea is to produce a set of initial programs that are, diverse, that explore different possibilities, but that are still, likely to be relevant to the task at hand.
Okay, so they're already thinking about diversity and exploring different options right from the beginning.
Yes, exactly. It's not about putting all their eggs in one basket, so to speak. They're casting a wide net at the start.
Makes sense. So what's the next step after generating these initial candidates?
Right. So the next stage is where the execute agent comes in. And this one's pretty straightforward. It takes those candidate programs, compiles them if necessary, and then runs them against a set of input-output pairs for validation. So it's basically checking, does this code actually produce the expected output? And it captures the standard output and standard error streams from this execution and assigns a score based on how well the program's output matches what's expected. And a key detail here is that if there's any output to the standard error stream, whether during compilation or execution, the program immediately gets a score of 0. So basically any kind of error is back to the drawing board.
That's interesting. So even minor errors or errors that might not necessarily prevent the code from running are still penalized.
Exactly. They're really aiming for perfection here, for code that's truly robust and reliable.
Okay, so what happens if a program fails some of these tests? How does the system learn from those failures?
Well, that's where the instruct agent comes in. And this is where the feedback loop really starts to take shape. So based on those input-output pairs that failed, and any error output that was generated, the instruct agent creates specific debugging instructions for another LLM, denoted as pdebug. And they've actually explored 2 main ways to design this agent. Instruct static, which relies on predefined templates. They give some examples of those in figure 3, and instruct LLM, which can either use a separate LLM, PEXplain, or those same static templates to figure out what instructions to give. So basically, it's about translating those errors into actionable feedback for the debugging process.
So it's like the instruct agent is saying, hey, this is what went wrong, and this is what you need to focus on fixing.
Exactly. It's providing guidance to the next stage, which is where the debug agent comes in. And this agent takes those instructions from the instruct agent, uses an LLM pdebug, which might be the same LLM as the synthesizer or a different one, and its job is to generate repaired versions of those candidate solutions. So it's like it's taking those instructions, understanding what needs to be fixed, and then using its knowledge of code to actually implement those fixes. Makes sense. So we've generated initial candidates, we've run them, we've identified errors, and now we've tried to repair those errors. So what's the final step in this whole process? So the last stage is where the rank agent steps in. And its role is to select the best performing programs from the current set based on their correctness, basically, how well they match the input-output pairs in the validation set. And to do this, they use what are called parent selection algorithms, which are inspired by evolutionary computation. So they specifically look at tournament selection, where programs are ranked by their average performance across all those test cases, and lexicase selection, which prioritizes programs that fully solve individual test cases, even if their overall average score might be a bit lower. And what's really interesting here is that they found that while those selection methods are important, the quality of the debugging feedback that's given to the LLM has a much bigger impact on the final outcome. So in other words, if the LLM gets the right instructions, if it knows exactly what to fix, it's much more likely to produce a correct solution, regardless of which program it started with.
Wow, so that's kind of counterintuitive. You'd think that choosing the best performing programs to build on would be super important.
Yeah, it seems that way, but it turns out that the clarity and accuracy of the debugging instructions are even more critical. It's like if you give the LLM a clear roadmap for fixing the errors, it can do amazing things.
That's fascinating. So zooming out a bit, how do the authors connect this AI Day framework to broader concepts in the field?
Well, they explicitly point out that while they've described it as a multi-agent system, you can also view it through the lens of evolutionary algorithms or even genetic programming. So from that perspective, the LLMs are handling the initial creation of the code, that's the initialization phase, and then they're doing those subsequent modifications based on the feedback, that's like the mutation step.
Okay, so it's like this population of programs that's evolving over time with the LLMs driving both the initial generation and the refinement process.
Exactly. And they also delve into this really interesting concept of a repair-replace trade-off, which is controlled by two key hyperparameters. N, the total number of candidate programs in each generation, and W, the number of repaired programs that are selected to move on to the next generation. They illustrate this really nicely in Figure 4. On one extreme, if both N and W are 1, you have a pure repair-only strategy, which they liken to a guided random walk. On the other extreme, if N and W are effectively infinite, you have a replace-only strategy, which is more like random sampling of new programs. And they emphasize that those strategies that fall in between those extremes with varying triarities resemble those population-based evolutionary algorithms. And they even draw this cool analogy to tree search and beam search, which are common search algorithms in computer science. And what that analogy highlights is how SEIDR is exploring the space of possible programs.
Okay, so it's like navigating a maze, trying different paths to find the solution.
Yeah, and what they find is that finding that balance between exploration and exploitation is crucial. The extreme strategies, they're just not as effective.
Makes sense. So before we dive into their specific experiments and results, I think it's worth taking a moment to look at how they position their work within the existing research landscape.
Yeah, definitely. And they do a really good job of that in their related work section. They note that traditionally, neural program synthesis and program repair have been treated as separate research areas, but they, along with others in the field, are working to bridge this gap by utilizing LLMs. They cite some really relevant work here from Joshi et al., Gupta et al., again, Fan et al., and Zhang et al., all around the same time frame. And they also contrast their approach with others like ELM, that's evolution, through large models by Lehman et al. In 2022, which focuses more on creative exploration and program generation rather than targeted bug fixing.
Right, so some approaches are more about like exploring the full space of possibilities, while SEIDR is more focused on efficiently finding a solution that actually works.
Exactly. And they also draw this interesting parallel to conversational agents that are used for code repair. They cite work by Zhang et al. In 2023 and Deng et al. In 2024. And they also mention iterative synthesis approaches from Chen et al., Xin et al., Xian et al., Xiandal, Jian et al., and Zelikman et al., all from 2023. And what's really interesting here is that SEIDR, it uses a fixed algorithmic structure, while some of these other approaches are exploring the idea of self-evolving algorithms. And they connect this to this long-standing challenge in genetic programming of finding what's called effective inductive bias, which was discussed by Wiggum back in 1996. And they propose that LLMs offer this really interesting alternative to traditional grammatical evolution methods, citing work by Reuter et al., Bartoli et al., O'Neill et al., and Custode et al. And the key point here is that LLMs, they don't just encode the grammatical rules of programming languages. They also capture the semantic understanding, the common patterns, the way experienced programmers actually write code.
Right, so it's like they have this deeper understanding of the intent behind the code, not just the syntax.
Exactly. So to really evaluate the effectiveness of this SEIDR framework, they designed their experiments to address 4 key research questions. The first one, RQ1, focuses on exploring that repair-replace trade-off that we talked about. So what they want to know is, what impact do different tree search strategies have in this autonomous programming context?
Okay, so that's about finding that sweet spot between exploring new options and refining existing ones.
Right. Their second question, RQ2, is about generalizability. So they're asking, how well does SEIDR perform when we use different LLMs and when we apply it to different data sets of programming problems? So they're really trying to see how robust this framework is.
That makes sense. You want to know if it's just good at solving a specific type of problem or if it can handle a variety of challenges.
Exactly. The third question, RQ3, deals with the repeatability of the results. Given that LLMs are inherently non-deterministic, meaning they can produce different outputs even with the same input, they want to see how consistent are the outcomes when we run SEIDR multiple times using the exact same hyperparameters.
Right, because if the results are all over the place, it's hard to know if the system is actually learning or if it's just luck.
Yeah, exactly. And then the final research question, RQ4, focuses on the parent selection strategy within the rank agent. They want to compare lexicase selection to the tournament selection they used initially and see which one performs better.
Okay, so those are their 4 key questions. So what data sets did they use to evaluate their framework?
So they chose 2 main benchmarks for their evaluation. The first one is PSB2, the Program Synthesis Benchmark 2, which Helmuth and Kelly developed in 2022. They use both the C++ and Python versions of this benchmark, and they picked it because it's designed to resemble those small, real-world programming tasks, and it includes a good number of test cases for each problem.
Okay, so it's not just like toy problems, it's actually representative of the kinds of tasks programmers might encounter in the real world.
Yeah, exactly. And the second data set they used is Human Evil X from Zheng et al. In 2023. This one is an extension of the original Human Evil dataset, which is a very common benchmark for evaluating code generation in LLMs. Human Evil X provides translations of these human-written programming problems and their tests into different programming languages, and for their research, they focused on the Python and C++ subsets. They point out that PSB2 has a large set of tests that are used during training and testing, while Human Evil has a more limited set. For their experiments with PSB2, they use the training set for validation within the SEIDR loop, and then they use the separate test set for that final performance evaluation. For Human Evil X, since there are fewer tests, they included some of them in the initial prompt, and they made all of them visible to CI during the debugging process, so they didn't have a separate held-out test set in the same way as PSB2.
Okay, so that's a key difference between the 2 data sets. With PSB2, they had a clear separation between training and testing data, while with Human Evil X, they used all the available tests for both training and evaluation.
Precisely. Now, in terms of the LLMs themselves, they started with Codex Edit and GPT-3 for their initial exploration. Both of these are massive models, 175 billion parameters each. But for their generalizability experiments, they shifted to GPT 3.5 and Llama 3. They mentioned that GPT 3.5 is optimized for conversational interactions and is available through an API, while Llama 3 is open source and uses a similar transformer architecture. And this switch was partly because of the rapid progress in the field, and that support for some of those older models was discontinued, but it also reflects their focus on evaluating how well their framework generalizes.
Right, so they wanted to see if their approach could work with different types of LLMs, not just the ones that were specifically designed for code generation.
Exactly. And their prompting strategies are worth mentioning as well. In their early experiments, they used static prompts built from templates with placeholders for details about the problem, the candidate code, and any error information. For the later experiments with those newer models, they adjusted those prompting strategies accordingly. And when they were looking at that repair-replace trade-off, they used different hyperparameter settings for the initial experiments with Codex and GPT-3 compared to those later generalizability experiments with GPT 3.5 and Llama 3. As they detail in Table 1, for that initial phase, they used wider intervals for the tree arity parameter and a higher maximum number of generated programs up to 1,000, and ran each configuration only once. But for the generalizability phase, you can see in Table 2, they used a more granular grid search for tree arity, limited the maximum programs to 100, and importantly, they ran each experiment 6 times to account for the variability in the LLM's outputs.
Okay, so they're really being rigorous here, trying to account for the randomness inherent in working with these LLMs.
Absolutely. And to measure SEIDR's performance, they use a few key metrics. First is the test pass rate, or TPR, which is simply the percentage of test cases that a generated program passes. There's pass at K, which is a common metric in code generation, and it tells you the percentage of problems for which at least one correct solution was found within K attempts. And lastly, they use excess programs generated, or EPG, which is the number of programs generated by SEIDR before finding that first completely correct solution for a given problem. They clarify that TPR is used for the final evaluation of a solution, but the rank agent might use a different scoring system that considers partially correct solutions. And they also explain why a specific statistical adjustment used with Codex's pass at K wasn't applied to their CD results. That's because of the iterative Markov chain nature of their framework.
Right. So the choice of metrics is really important, and they're making sure to use ones that accurately reflect the performance of their system.
Exactly. Now, diving into the implementation, they used a llama and LangChain to interact with those different LLMs. And they also varied the temperature parameter during the sampling process when generating candidate solutions. This was done to encourage diversity in the generated code to explore more options.
Okay, so let's finally get into the results. What did they find in that initial exploration of the repair-replace trade-off, RQ1, using Codex and GPT-3 on PSP2? Figures 5, 6, and 7 summarize their findings there.
One of the big takeaways was that SEIDR, when paired with Codex, actually outperformed the PushGP baseline in Python, and it did about the same in C++by when they used a tree arity of 10. Just so you know, PushGP is a genetic programming system, a strong baseline for this type of problem. It managed to solve 17 of the 25 problems in PSP2 in their evaluation.
So SEIDR is already showing some really promising results compared to existing approaches.
Yeah, definitely. And another interesting finding was that those compromise strategies, tree arities of 10 and 100, perform better than those extreme repair-only or replace-only approaches. It seems like the repair-only approach just didn't explore enough of the possible solutions, while the replace-only strategy was too random and didn't benefit enough from the feedback.
Right, so it's all about finding that balance.
Exactly. And they found that a tree arity of 10 led to the best results overall, suggesting there's an optimal balance point between exploration and exploitation. Looking at the EPG values, they noticed that many solutions were found very early on with an EPG of 0 or close to it. This tells us that those initial steps of code generation and debugging are super important. They also observed that the chance of finding a correct solution dropped significantly after generating a lot of programs.
So the early stages of the process are crucial, and it might not be worth spending too much time on a problem if a solution isn't found relatively quickly.
Yeah, that's what the results suggest. And when they looked at individual problems, they saw that some were solved in both Python and C++A, while others were only solved in Python. There were also a few problems that they couldn't solve at all, and they did some qualitative analysis to try and understand why. Some of the potential reasons included logical errors in the generated code, problems understanding the test case requirements, or issues with how the code was handling input.
Okay, so that's really interesting. It's not just a matter of the framework itself. There are also inherent challenges in the problems they're trying to solve.
Exactly. Now, moving on to the generalizability experiments, RQ2 and RQ3, where they used GPT 3.5 and Llama 3 on both PSP2 and human evil figures 8 through 12, give us a good overview of their findings.
Okay, so they're testing with newer models and different data sets now.
Right. And one thing they noticed was that the results for Python were more consistent across those 6 repeated runs than the results for C++A. They think this might have something to do with the amount of Python code in the LLM's training data, but more research is needed to confirm that.
Makes sense. The more data the LLM has seen, the more likely it is to perform well on similar tasks.
Yeah, that's the idea. Overall, GPT 3.5 did better than Llama 3 on PSP2 in both Python and C++ lenties. But interestingly, there was a drop in performance compared to those earlier experiments with Codex. SEIDR with Codex solved more problems in both languages at a tree arity of 10 than the best results they got with GPT 3.5. The author suggests this might be because those newer models are more focused on general knowledge and a wider range of tasks, while Codex was perhaps more specialized for code generation. They also acknowledge that the lower limit on the number of programs they use with GPT 3.5 might have played a role.
So it's like a trade-off between generalization and specialization.
Yeah, it seems like it. In these generalizability experiments, they consistently found that moderate to smaller tree arities, 16 or less, worked best, but there wasn't one magic number that worked best in all cases. Looking at how quickly they found solutions, GPT 3.5 was generally faster in Python. They also reported a significant number of unique human evil problems solved by both GPT 3.5 and Llama 3 at least once across all their runs. And their figure 13 reinforces the idea that those early iterations are super important.
Okay, so let's move on to their findings on parent selection strategies, RQ4. They focused on lexicase selection as an alternative to tenement selection. Table 3 and figures 14, 15, and 16 detail what they found.
Interestingly, they didn't find one ranking strategy that was always better based on average TPR and the number of problems solved. But there were specific cases, especially with GPT 3.5 on C++A, where Alexa case selection improved the number of runs it took to find a solution. However, the most striking finding, and they show this in Figure 16, is that most of the time, a program's test score jumps straight from 0% to 100% correct. This tells us that having a good prompt in that debugging loop, one that clearly identifies the error, is probably much more important than which parent program was selected for the next round of debugging. If the LLM knows exactly what needs fixing, it's more likely to get it right, regardless of which slightly flawed program it started with.
So again, it comes back to providing clear and specific instructions to the LLM.
Yeah, that seems to be a recurring theme. Now, to wrap up their findings on generalizability, they give a nice summary in tables 4 and 5, where they compare SEIDR's performance in terms of pass at K and the number of problems solved at least once with the PushGP baseline on PSP2, and with other LLMs without SEIDR on Human Evil X.
Okay, so they're comparing SEIDR to both traditional approaches and other LLMs.
Exactly. One notable finding is that CR with Codex actually achieved a higher pass at 1000 on PSP2 Python than GPT 3.5's pass at 100. His CR with Codex also solved slightly more PSP2 problems at least once compared to GPT 3.5. And in C++R with Codex, also beat the other LLMs they compared it to on PSP2.
Yeah.
But across all their PSP2 experiments, they didn't find a single parent selection strategy or triarity that was consistently the best. Interestingly, on Human Evil C++RC, his IDRA performed really well, particularly at higher values of K, which shows the benefit of that iterative debugging process. Combining the results from all their SEIDR runs, using both GPT 3.5 and Llama 3, they managed to solve a very high percentage of the Human Evil C++ problems. However, they did note that SEIDR didn't do better than those other LLMs on Human Evil Python. They speculate that this might be because Human Evil Python is a very popular benchmark, and those other LLMs might have been indirectly optimized for it during training.
So it's possible that the other LLMs had a bit of an advantage on that particular data set.
Yeah, that's what they're suggesting. They also acknowledge that directly comparing SEIDR's performance to other iterative program synthesis frameworks is tricky because of differences in the benchmarks and the metrics used.
Right, so it's not always an apples to apples comparison.
Exactly. Before wrapping up the main discussion, they talk about potential threats to the validity of their findings. They mention external threats, like whether their results would hold up with other benchmarks and other LLMs, and internal threats related to their implementation and the randomness of LLMs. They did things like using the diverse test cases in PSP2 and running multiple experiments with the newer models to address these threats. But they also acknowledge limitations like only running the experiments with Codex and GPT-3 once due to cost, and the fact that support for those models ended.
So they're being transparent about the limitations of their study, which is important.
Definitely. To sum up their contributions, they provide a detailed look at the SEIDR framework. They explore the repair-replace trade-off. They evaluate SEI with various LLMs and datasets, and they analyze the effects of different ranking strategies. They found that a balance between repair and replacement, a triarity around 10, works well, and that SEI has a lot of potential for autonomous programming, especially on Human Evil C++I.
So this deep dive into the work of Grasina and her colleagues reveals a really interesting and potentially groundbreaking approach to automatic programming. The SEIDR framework, with its multi-agent system and iterative refinement process, offers a promising way to overcome those limitations of current code generation techniques.
To you, our listener, think about what it would mean to have a system that can not only write code, but also debug and improve it all on its own. How could this change the way we develop software? What new possibilities could open up if it becomes much easier to create software?
And here's a final thought. The paper mentions LLM-based agents working together on software engineering tasks. Imagine a future where not just code generation and debugging, but also things like gathering requirements, designing the system, and even testing are all handled by intelligent agents. What challenges and opportunities might that bring?
Don't forget, this is a field that's moving incredibly fast. While this paper's results are promising, fully autonomous programming is still a work in progress. Our discussion today was for informational and entertainment purposes only.
We've only scratched the surface of this research in our deep dive. The paper goes into much more detail about their experiments, results, and analysis. We encourage you to check out the full paper. We'll link it in the show notes. What aspects of autonomous programming are most interesting to you? What future directions do you see emerging from this work? We'd love to hear your thoughts.